Hello everyone, and welcome to the video on the fundamental theorem of algebra. This is for chapter 2 section 5. The skill objectives for this video are 1. Find complex zeros of a polynomial. Number 2, use the complex conjugate zero theorem. And number 3, factor polynomials over the complex numbers. Our conceptual objectives on this one. We want to extend the idea of the domain of polynomials to the complex numbers, to include complex numbers. Number 2, we want to understand how the fundamental theorem of algebra guarantees at least one zero. And number 3, understand why complex zeros occur in conjugate pairs. So that's where we're at, and so we can get started now. Before we move into the fundamental theorem of algebra, I just want to make sure everybody has the same understanding of what a complex number is. Complex numbers are also known as as imaginary numbers. Those are the ones, a lot of times when people talk about complex numbers, they say that, oh, it's the ones that have the i's. So a complex number can be any number that can be written in a plus bi form, where I represents the square root of -1. So that would be a complex number. So some common ones that we can all look at, we see these over here. We say, oh, those are complex numbers. You see the I in them. Okay? And a lot of times when people look at these, they say, oh, these are not complex numbers. These are real numbers that we see all the time on the number line. Well, the key to this definition is right here, that it can be written in the a plus bi form. Now, also remember, a and b are also going to be real numbers. So what happens here, like 6, I can think of 6, that number 6, as 6 plus 0i. So 6 is actually a complex number. In fact, all of those over here, every number you see on here, that's 1/2 plus 0i, and the square root of 3 plus 0i. In fact, every number that you have ever worked with, every number that I have ever worked with, every number that any individual on this planet has ever worked with has been a complex number. Every number is a complex number. Let me repeat that. Every number is a complex number. You cannot identify a number that would not be a complex number because of the fact that any number that can be, as long as it can be written in that form, it is a complex number. So if you don't see an I, you can just say, oh, plus 0i. Now we get to the fundamental theorem of algebra. This sounds big, and it is kind of a big one. And the fundamental theorem of algebra is what you see in blue on this slide. And it says that every polynomial of degree n greater than 0 has at least one zero in the complex number system. So in other words, every polynomial, I can find one complex number, at least one complex number that will make a polynomial equal to 0. It could be a real number, something that shows up on the number line, or it could be a complex number, anything that has an I in it. Now we know from the previous section that when I go through and do synthetic division, so if I was to do a synthetic division problem right here, I'd have this information there, and that remainder would go there. If I put a 0, something that is going to make the polynomial equal to 0, so call it C, I'll have those coefficients of my polynomial there. If that's 0, then I know that these represent another polynomial, and the degree of that polynomial that's going to be represented right here, the degree is going to be 1 less than what I started out with. So, because of that, now we have another polynomial. And again, by the fundamental theorem of algebra, I know that polynomial right here, whatever that one is, would also have at least one zero in the complex number system that I could find. And I can go through this over and over, and the end result really comes down to the N0 theorem that we have in red here. So this is kind of a consequence of the fundamental theorem of algebra. And what that says is Every polynomial of degree n greater than 0 can be expressed as the product of n linear factors in the complex number system. In other words, if I have a second degree polynomial, I can write it as the product of two linear factors, x plus or minus whatever those zeros happen to be. If I have a cubic, a third degree polynomial, it can be written as the product of three linear factors. And again, the zeros could be any complex number, any number I want. So it could be something that's on the number line, or maybe it's something that is in the complex plane. If it's a fifth degree polynomial, it can be expressed as a product of five linear factors. So what we're going to end up having you do is I'm going to end up, the end product on this is I'm going to give you a polynomial. And I'm going to ask you to write that polynomial as a product of linear factors. In other words, I'm going to ask you to completely factor that polynomial, and you're going to factor it over the complex number system. So we could have real zeros, we could have imaginary zeros. You're going to have to find all of them. So if I have a 6th degree polynomial, you know you're going to have to find 6 zeros. One of the things we have that can help us out with this is the complex conjugate zero theorem. Okay, and what that says is if a polynomial p of x has real coefficients, so as long as it's real coefficients, the coefficients are real numbers, anything we want, and if a plus bi is a zero of p of x, then we know its complex conjugate, which is a minus bi, is also a zero of p of x. For those of you who are not familiar with the word conjugate, basically what you're looking at here is, look at the sign here, a plus bi and a minus bi. Those are conjugates. The only difference between them is the sign that's between them. So what we have here is I have on this page is 4 complex numbers, and what we want to do is write down the complex conjugate of each one. So what I'd like you to do now is pause the video and write down what you think would be the complex conjugate of all 4 of the numbers. So I have 2 plus 3i, 4 minus 7i, negative 3 plus 5i, and negative 2 minus 6i. So pause the video, write those down, and when you come back, we'll go through what the complex conjugate of each one of those numbers really is. Welcome back. Hopefully you now have gotten those, and let's see how you did. The complex conjugate for 2 plus 3i, remembering what's really changing here is the sign between the two pieces of the real portion and the imaginary portion of the complex number. So in this case, for 2 plus 3i, the complex conjugate is going to be 2 minus 3i. Notice the only sign I'm changing is the one between the 2 and 3. It doesn't change the sign on the 2. The complex conjugate for 4 minus 7i is going to be 4 plus 7i. The complex conjugate for negative 3 plus 5i is negative 3 minus 5i. And the complex conjugate for negative 2 minus 6i will be negative 2 plus 6i. So hopefully you got those correct, and if not, take a look at those and make sure you understand why you missed them, and make sure you understand what you should have done. Now, often the question is for people is, why is it that the complex zeros occur in these conjugate pairs? Well, here's the reason why. The only way that you are going to actually be able to locate a complex zero is going to be through the quadratic formula. And think about the quadratic formula for a second. It is minus b plus or minus that square root, the square root of the b squared minus 4ac. That plus or minus in there really is indicating that you're going to be finding conjugate zeros. So that's why you end up with conjugate zeros when they're complex. And also, if you're working with integer coefficients, why the irrational zeros will also be in conjugate form. Now let's take a look at a couple examples. the first one, example 1, we want to find a third degree polynomial that has zeros at 2 and we have one at negative 3i. Well, the first thing I want you to realize on this, not only do we have a 0 at negative 3i, but because of that last theorem that we had, that they come in conjugate pairs, I know another 0 on this is going to be 3i. So I actually have those 3 zeros, so I'm going to I want to be able to go and find a polynomial that will have 3 zeros. The 3 zeros are 2, negative 3i, and 3i. Well, to do this now, what we have to do is write it out in its factored form. Well, one of the things I will also remember is that I know if a number is a 0, then x minus that number is a factor. So since 2 is a 0, since that 2 is a 0 there, I know that x minus 2 is a factor of that polynomial. Since negative 3i is a 0, I know that x minus the negative 3i, which would be plus 3i, is going to be one of my factors. And since 3i is a 0, I also know that x minus 3i is going to be a factor. Now to actually go and identify what that polynomial is, if I'm being asked to multiply it all out and get it into the form that we usually see a third degree polynomial in, what I'm going to have to do is I have to go and multiply this out. So my suggestion to you, although it might seem like it's something you don't want to do, a lot of people sit there and say they don't want to deal with the i's, they want to avoid it as much as possible. But I'll tell you what you want to do is really start out by multiplying those two together, the x plus 3i and the x minus 3i. The reason we want to do that is if you do it correctly, when you multiply out the factors that have conjugate zeros, if you do it correctly, the i's will drop off. So what I'd like you to do right now is pause the video, and I'd like you to go and multiply out the x plus 3i and the x minus 3i. Keep that x minus 2, bring that down, but let's multiply out those last two and simplify it as far as you can. And when you come back, we'll go through what the answer should be. Welcome back. Now, in this case, what I did on this one, I want to first FOIL out these. So I'm just going to use the usual standard FOIL process. And when I multiply this out, when I FOIL that out, I get x squared minus 3ix plus 3ix minus 9i squared, because it's the negative sign there. And 3 times 3 is 9, and I times I is I squared. Now, what you have to remember on this is that we know I is equal to, I equals the square root of negative 1. So therefore, when I square I squared is going to equal a negative 1. So that's why when I simplify this, the 3ix and then minus 3ix, those cancel out. And that I squared, since it's negative 1, this whole thing right here is going to become x squared plus 9. So now I have x minus 2 times x squared plus 9. And when I multiply that out and then put it into the standard descending order, I get x cubed minus 2x squared plus 9x minus 18. Take a minute. Make sure that you are comfortable with everything that I did here. And if not, make a note of it to make sure to ask about in class next time. Next example is that they're going to ask us to go, they're going to give us a polynomial, and they're going to want us to write it as a product of linear factors. In this case, we have a 4th degree polynomial, so I need to find 4 linear factors. Okay. Now, here's what I really need to know. I have to keep in mind. Number one, I need to try to identify 2, because if I can find 2 zeros, I can use synthetic division to get this down to a quadratic, and I can find the last 2 zeros using the quadratic formula. So let's start out. What you're going to want to do with this is, the first thing you want to do, what I tell people to do on this, is to graph the polynomial. So what I'd like you to do right now, pause the video and graph p of x equals x to the fourth minus 2x cubed minus 2x squared minus 2x minus 3. Now that you have the function graphed on your calculator, if you look at it in the standard window, you can look and you probably can identify where it looks like two places where it looks like the graph crosses the x-axis. Now I'm looking at it, what I see is it looks like it crosses one at -1 and the other at a +3. So what I'm going to do now is I'm going to go and I'm going to use synthetic division to go and identify, make sure that these are zeros. So to start out with here, we'll start out with dealing with -1. So I make the usual chart. I'll put a -1 there. And then it's going to be a 1, -2, another -2, another -2, and then finally a -3. And so in this case, the 1 comes down. -1 times 1 is -1. Add it up, I get -3. -1 times -3 is 3. Add it up, I get 1. -1 times 1 is -1. Add it up, I will get -3. And -1 times -3 is 3, and I add it up, I get 0. So in this case, -1 is a 0. And so one of my factors is going to be, from this I know that one of my factors is going to be x minus a -1, which is actually equal to x plus 1. So one of the linear factors I have is x plus 1. The next thing I want to do is I'm going to go and use synthetic division again, but like we did in class, I am now going to go from this result here. I'm going to use synthetic division on this. Now I do know that I had another 0. It looked like it was at 3. So what I'm going to do is I'm going to set up the symbol that we have, and this time I'm going to put the 3 here. So now when I run through, the 1 is just going to come down. 3 times 1 is 3. Add it up, I get 0. 3 times 0 is 0. Add it up, I get a 1. And 3 times 1 is 3. Add it up, I get a 0. So in this case, that is also a 0. 3 is also a 0. And so I know another factor of this polynomial is going to be x minus 3. So I have two of the factors. The other thing I have now is that the result that I have here is now a quadratic, and it is the quadratic x squared plus 1. So what I need to do is I need to just solve that one. I just set it equal to 0. This one's a real easy one to solve. I'll set it equal to 0. And so from there I can go and solve. I subtract 1. I get x squared equals -1. So x equals plus or minus the square root of -1, which equals positive and negative I. So in this case, I know that I and negative I are zeros. So my other two factors from this would be x plus I and x minus I. So my four linear factors, in this case p of x, I know is equal to x plus 1 times x minus 3 times x plus I times x minus I. And that now is, that polynomial now is in its completely factored form. This now concludes the video on the fundamental theorem of algebra. Make sure you are comfortable with this process because you're going to use this a lot in 2.5. We'll also talk about, in class, we'll talk a little bit about ways to go and have a better idea what type of zeros we're going to be looking at. But for right now, this is the process I would like you to be familiar with and be ready to use. And this, what I've shown you here, would be successful on any of the problems you're going to have to do in class. So hopefully everything went well and you feel comfortable with this, and you have a good evening, and we'll see you at our next class.